Hi friends, welcome. This is the fourth video lecture on BJT. Till now we have completed, in the last video lecture we have seen some problems. Today also we'll start with problems only. The problem is based on the potential divider. But before that I would like to tell you that in this complete entire unit we have seen the output characteristics of the BJT, biasing of the BJT. In the last video lecture we started biasing, fixed bias, we have seen emitter collector feedback, emitter resistor biasing, potential divider biasing we have seen the stability factor also. Why we are choosing the biasing such that we can use the BJT in the active region, so we can get the amplification. As earlier I told you that BJT is always work in three region. The first one is active, second saturation, and third is cutoff. The saturation and cutoff is like switching. Okay, these two things for switching applications. Cutoff means zero output, saturation means very high output. So for the amplification purpose we need to work a transistor in, for the amplification we need active region. So we discuss about that. The most important thing we have done is to find out the region of operation, because we are having 3 to 4 questions in GATE from that particular question only. Later we'll see some more problem on that concept only also. So friends, let me tell you one thing. Today also I'll start the session with problem only. So let's start it. Let me take fresh page over here. Okay. The problem is given. Wait a minute. The problem, first of all, I'll tell you this is the GATE problem in the year 2002 and 2 marks problem. Okay. And the problem is, I'll take 30 seconds to write. 2.2K connected with 5 volt. Fine. This is 4K over here. And this is 300 ohm connected with 1K. This is grounded. Here this is they are saying this is minus and this is plus, and in between them obviously we are having VCE. Here in the circuit I have IC. Everything is correct now. Yes, perfectly fine. Now come to the question part. What they are asking to us. They are asking, assume that the beta of the transistor is extremely large. Beta of the transistor is very large. Perfectly fine. And VB is 0.7 given over here. Always it will be given. IC and VC in the circuit shown in the figure are, they're asking. In this circuit only two variables are looking to us, and that is IC and VCE. Okay, so the options are given. IC equal to 1 milliampere and VCE is equal to 4.7. Option B is given. It's 0.5 milliampere and 3.75 volt. Option C is given 1 milli and 2.5 volt. And the last option is 0.5 milli having 3.9 volt. So this is the question given. This is the potential divider biasing. Okay. So if you don't know this is a potential divider biasing, you should know that how to proceed. It's enough. Okay. See, this is the input. I can take the equivalent circuit of the input. Can I? Yes, I can. See, this is collector part 2.2K connected with 5 volt. Everything is okay. Over here you are having 300 ohm and your circuit is like this. Now for this I need equivalent circuit. I need voltage at this point. So I'll find the voltage across 1K, and voltage will be 1K into 5, this is the source, divide by 4K plus 1K, and that is why I'm doing so, because see they are connected in series. This is the obstacle. Here the current is 0. Why? The beta is very large, right? So it's a very low current, very minimum current. So we can take there in series circuit, no problem at all. That's why I'm dividing potential. So 5 into 1k divided by 5k, k will cancel. It will be 1 volt over here. So it is 1 volt. I have to replace this equivalent resistance also, and it will be, they are connected in parallel combination. When we will do it DC or we will do it grounding like this one, so this is the common part in between them and this is the common part. So they are connected in the parallel now with respect to this terminal I'm talking about. Okay. So 4k into 1k divided by 5k. So it will be 4 by 5k. Is it okay? Your circuit is like this. Now they're asking find IC and VC. This is simple circuit right now. Now you have to check whether it's working in saturation or inactive. So proceed whatever I told you in the last time how to proceed this type of problems. You have to first find out the IC saturation. IC saturation you have to find out. IC saturation will be 5 divided by 2.2 and 3, so 2.5k. So it will be 2 milliampere. Your IC saturation is 2 milliampere. Equation 1. It's fine, perfectly fine. Now we'll come with this, right? So this is 1V, 1 volt and 1 volt, and there is a no drop in it because IB is 0 for very high or large value of beta. Here I'm getting minus 0.7 and here I'm getting 300 into IE equal to 0. This I equal to IC over here. Last time I told you this concept that whenever beta is large, IB will be 0. When IB will be 0, IC equal to IE, if you remember. So it will be 0.3 divided by 0.3 equal to 300 of IC. IC is equal to 0.3 divided by 300. So it will be 1 milliampere. So this is your IC active. So what is the relation? I saturation is greater than I active. Perfectly fine, no problem at all. So your system is working in active mode. If it's working in active mode, your IC current is 1 milliampere. Let me erase some parts so it will be clear to see it, right? Now you identify that your BJT is working in which region? It is working in active region. If it is working in active region, so what is the IC active? You calculated IC active is 1 milliampere. Now, no more this circuit is working in the saturation. You check the condition, right? This is very essential to solve this type of circuit. Please check whether it's working in saturation or in active region, right? So your IC active you calculated, and that is 1 milliampere. Perfectly fine. Now he is asking for YC. IC is 1 milliampere. We are having two options. Now we have to calculate VCE. If IC is 1 milliampere, here now I can remove this. This is no more. See, no longer exists this one. It is VCE plus minus. So you have to apply KVL in this outer circuit and you have to get the value of VCE. So you will start with the 5 and the minus 2.2k of current is 1 milli minus VCE minus 300 of IE, and that is 1 milli itself equal to 0. So VCE you are interested in to calculate. So VCE will take that side. It will be 5 minus 2.2 minus this thing will be 0.3. So it will be 2.5. So VC equal to 2.5. Do we have any option in which IC is 1 milliampere and VC is 2.5? Yes, we are having option C. So you have to take option C. So this question will take hardly 1 minute to 1.5 minutes and you will get 2 marks. Okay. So please try to understand that while proceeding this directly at the input stage, first check at the output stage for saturation, first check the condition, then only answer the question. Okay. If you will do it wrongly, you will directly calculate IC. What if your IC saturation, your IC active is suppose 2 milliampere. You calculated from the input stage. Your 2 milliampere will be there in the option, and based on this you calculated your VCE also. That was also a wrong value you calculated. Okay. If IC active is 2 milliampere and IC saturation in real is 1 milliampere, and you are proceeding to this way, it means it's completely wrong. You are going in the wrong direction. So please be careful whenever you get this type of question. Please follow the rules. Please follow the steps. And the steps are, the very first step, you have to check for IC saturation. You have to calculate IC active, then compare. If IC active is greater than IC saturation, then system is working in the saturation. If IC saturation is greater than IC active, then system is working in IC active. Is it okay? Let's come to the next question. This is the question, came in 2013, GATE 2013, 2 marks. Okay, and the question is, let me draw it. I'll take only 30 seconds. Don't worry. Here this is 500 ohm. Again, potential divider by seeing 60K connected over here, and it has 3 volt VCC connected with R2, and R2 is unknown variable. This is all about the circuit. They are giving the options 20, 30, 40 and D 50. Now what is the question? Come to the question now. Let me change the pen. Okay. The question is, in the circuit shown below, this is the circuit, the silicon NPN transistor they consider NPN, so it will come out, and has a very high value of beta. The beta is high. The beta is high means IB is 0. It means IC is equal to IE. By default we have to consider it. Forget about IB when beta is high. Is it okay? So what they're asking, the required value of R2. They're asking the required value of R2 to produce IC equal to 1 milliampere. What is the value of R2? So it can produce the value IC is 1 milliampere, and they're asking R2 in kilowatt only. Kilo ohm only. Okay. So friends, this is given to us that beta is very large, IB will be 0, IC equal to IE. And what they're asking, when IC equal to 1 milliampere, what will be the value of R2? So friends, let's take IC equal to 1 milliampere. Okay. So if IC equal to 1 milliampere, it means emitter current I is also 1 ampere. Emitter current 1 ampere is by default. Okay. So 1 milliampere will come over here, it will drop, and the voltage drop across this point will be 0.5. 500 multiply with 1 milliampere, you will be having 0.5. This is VE. Is it okay? Now see, here is the voltage is V2. Okay, this is the R2, so I'm taking it V2. Now apply the KVL in this circuit. So here you are getting V2, perfectly fine. V2 is across this V2. V2 plus minus VBE you are getting over here, VBE. So VBE is 0.7. And you are terminating yourself at VE, because VE is given with respect to ground. So minus VE equal to 0. So finally you are having V2 equal to 0.7 plus VE. 0.7 plus VE. What is VE? VE you calculated 0.5. So this is 1.2. So your V2 is 1.2 volt. You calculated equation 1. Now you need to calculate the value of R2. What you will do? You will divide. You will divide the voltage. So voltage across R2 will be by potential divider circuit 3 into the value of R2, that is over here, divide by total resistance, that is 60K plus R2. This is nothing but the voltage across here, and we calculated it already, 1.2 volt. In this equation, is it okay to you? First you calculated V2 based on the assumption that your current in the circuit is 1 milliampere, that is IC 1 milliampere. IC is equivalent to IE, so 1 milliampere you have to consider V2 equal to 1.2. Is it okay? Now what next? What is the value of R2 if these two values are equal to each other? Okay, so we'll do it by, okay, this is 3R2, right? Let me take it 3R2 equal to 60K into 1.2 plus 1.2 R2. So when you will subtract 1.2 from 3, so it will be 1.8 R2 equal to 60 into 1.2 K. This 2 will 6 3 ja, 6 2 ja, right? And this 3 2 0. So finally you are having 40K. Your answer is 40. So 2 marks in 2 minutes. Is it okay? This is all about this question. I hope you are getting the concepts. I hope you are getting that how to solve the questions, how to apply. This is circuit, right? This entire subject name is analog circuit. Analog means instead of simple element, resistance and capacitor, you will be having some electronics device elements or electronics element like transistor, diode, FET and all. Is it okay? So now we will see some theory part. Okay. The emitter biasing. Okay, we didn't complete this portion, right? Emitter bias. Okay. So this is the emitter bias. RC here, RE in the base region, you are having only RB. Here we are biasing the emitter, means we are applying something to emitter, right? So this is the emitter bias. See, shown the emitter bias circuit, the circuit gets this name because the negative supply VEE is used to forward bias the emitter junction through resistor RE. See, we are applying here minus VEE to this emitter to make it forward bias. For all earlier biasing, we didn't have here any voltage across emitter. The emitter was always grounded. It may have some resistive component, but it was grounded. But here in this case, the name itself is saying that emitter is biased. Means you have applied something to emitter. You have applied some energy to emitter. Okay. So here we applied minus EE to make it forward bias. VCC still reverse bias. VCC still reverse biases collector junction, and because of this VCC, the collector junction is reverse bias. Okay. This also gives the same stability as voltage divider circuit, but it is used only if split supply is available. Okay. So this is the brief about emitter biasing. The application of this all biasing we will see in the numericals only, in the problems only. Okay. This is one problem I'm leaving for you. You can do it. This is the simple potential divider circuit. You can do it, but remember this is PNP type. So apply the things accordingly. And here you can tally your answer. Your current is 4.65 milliampere. You can note down it, please. For the circuit shown in the figure, calculate IC and VCE. This is the circuit given over here, 30. Here this is grounded, 2K, 3K, V out. You're taking V out over here, and you have to find IC and VCE. Okay. Your answer is given over here. So let me switch to the another. So before going to start the small signal analysis, this is the very important part, because 60% question we are getting from this portion only for this BJT unit I'm talking about. 60% questions we are getting from small signal analysis, or based on the idea on small signal analysis. So I'll start it. Before that, I'll give you, brief summary of the biasing. Okay. Wait a minute. So briefly we'll discuss what we have done till now. So friends, in the BJT, the current relation is always IE is equal to IB plus IC, as you know this. Is it okay? If you'll talk about IC, so IC is nothing but beta times of IB in general, because ICO is 0. Otherwise, the general formula is given by beta IB plus beta plus 1 of ICO, where ICO is the leakage current and this is in nanoampere. So this is negligible current. So IC is beta IB mainly. If I'll talk about IE, the relation between IE and IB is given beta plus 1 of I beta. Is it okay? So another parameter is there, that is alpha, and alpha is IC divided by IE. Alpha is IC divided by IE. So when you will be having relation in alpha and beta, so relation will be beta divided by beta plus 1. Is it? So alpha in terms of beta will be beta divided by beta plus 1. If you want to write beta in terms of alpha, it will be alpha 1 minus alpha. Okay. So here this beta we call the beta DC. Beta DC, if we talk about, it will be IC divided by IB. These are the DC current. At the same time, we are having beta AC also. If we'll talk about the beta AC, we'll take the change in current of collector, change in the base current. Okay. Similarly, see, this is alpha. Alpha is alpha DC. Alpha DC is nothing but IC divided by IE. If you have alpha AC, so you will choose the delta IC divided by delta IE. Okay. And for transistor, the very important formula or equation is IE is nearly equal to IC. Okay. And one more thing, if beta is very large, the IB will be 0 in the circuit. When IB is 0 in the circuit, IE is equal to IC. Correct? Now we'll see the biasing part. Okay. We've seen 4 types of biasing. The first one is fixed biasing. Fixed biased. Okay. In the fixed bias, the circuit is, let me draw the circuit for this. This is RC over here, like this, and from here this is VCC. From VCC to base I have RB over here, like this. In this IB will flow. Is it like this? And here with a capacitor I'll take V0. At the input stage also we have capacitor, and here I'll apply V in AC. Here I'll apply V in AC. Here I'll take V output AC. Is it okay? So this is fixed bias circuit. Okay. Later we'll see the same thing in the problems also. So there the doubts will be clear how to solve fixed biasing. Okay. Fixed biasing is over. Now I'll come with emitter stabilized biasing. Okay. In the emitter stabilized biasing, if you remember, I applied emitter resistance only. Okay. So for emitter biasing, the circuit is like, in the emitter I introduced RE and it was grounded. This is the collector portion. I'm taking V0, here RC, VCC, here RB as it is. Okay. Here we applied input part, V in. This is the AC. All over we are using it as AC, right? Next biasing will be voltage divider biasing. Okay. So let me clear it first. Voltage divider. Voltage divider biasing. Okay. And in the voltage divider biasing, the circuit is like, this is R1. Here it is R2. Like this. The transistor. Like this. Here I have RC. Here I'm taking V0. and this is RE also, emitter resistance, grounded, and here I applied VCC. Okay, so this is voltage divider biasing. In the voltage divider biasing, we reduced the circuit and we took the circuit, the equivalent of this, let me take R equivalent, and the voltage across R2, that is V2, like this. To this entire thing I converted into this equivalent form, and this is RE over here. Here I'm taking output V0, and here this is RC connected with VCC. This is voltage divider biasing, and in the voltage divider biasing the condition was beta RE should be equal to 10 of R2. Okay, so why we are doing this biasing? To keep IC independent of beta. To keep IC independent of beta, because beta is directly affected by temperature. So if you will make IC independent to beta, so automatically IC will be independent of temperature. So IC should be constant. For any active amplification, IC should be constant. This is first and foremost criteria. IC should be constant. Okay, so this is the voltage divider. Let's come to the collector feedback. Collector feedback biasing. Okay, in this biasing, from collector we are having one feedback. This is VCC. This is RE. Here taking output, and this is feedback, RF I'm taking. This is V. This is collector feedback biasing. Okay, so friends, this all biasing circuits will encounter in the problems. So there we'll calculate the voltage gain, current gain, input impedance, output impedance, and all parameters. Okay, and we have seen the configuration: common base, common emitter, common collector. So there I showed you in the symbolic representation like N, P, N. Earlier I told you, like, if you base will be common, then it will be common base, collector will be common, then it will be common collector, emitter will be common, then it will be common emitter. But here I'll show the circuit. Okay, for the common base I'll show you the circuit. The circuit will be, here it is RC, here it is R1, and this is RE over here, R2, capacitor, this is capacitor. Okay, like this, and here I'm taking V0. So where I'm applying V in, common base, the base is common, the base is common, like this, directly connected with ground. It will be like this one. Capacitor will be there, means you are grounding it. Okay, how it will ground, later we'll come to that point. So you have to apply input at emitter. So here this is V in. So this is the input stage, this is output stage. Means you are applying input at emitter and you are checking output at collector, because your base is common. Your base is common. Okay, so how to identify circuit? So suppose circuit is given to you and someone is asking, find out it's whether common base or common collector or common emitter. So friends, the terminal which is directly connected with capacitor and capacitor which connected with the ground is the common. Is it okay? Or in other words, you can see at this terminal you are applying input, at this terminal you are taking output, so remaining terminal is the common in between them. Is it okay? So this is the common base. Now I'll tell you some characteristics of common base. This is very important, so please remember it. Okay, let me take it. For the common base, this is the current buffer, okay? This is current buffer. Current buffer means the current gain of this circuit is 1. Output current, input current both are. If this is the current buffer, so this is current control current source. The current control current source. Current is controlled by the current input. Is it okay? Point number 1, point 2, point 3. Now the voltage gain is high in this 600 because current gain is 1, so voltage gain will be high. Okay. The next point is, so if we'll talk about impedance at input stage, it will be 30 ohm. Okay. Z at output, if I'll talk about, so it will be in mega ohms. Okay. The power gain AP is AI into AV. AI is 1. So it's nearly equivalent to AV. So these are the terms related to common base. Common base is the current buffer. So you can remember by the name only CB current buffer. AI 1. Its current control current source. AV is 600. Z input 30 ohm. Z output in mega ohms. AP, the power gain is AI AV nearly equal to AV only. These are the silent features about CB. Okay. Now I'll talk about the common collector. Common collector. Common collector configuration. In the common collector configuration, see RC, R1, R2, here I'm taking output V0. At the base I'm applying Vin. I'm sorry for this. So you can see here VCC. Here you can see, and one more thing I forget, the collector element will be connected in parallel with capacitor. This is the common collector. So two things we can judge whether it's common collector or what. You are applying input at the base, fine. You are taking output from emitter, fine. So by default collector will be common in between them. In another words, I can say if the capacitor is connected in parallel with the element of any of this base element or base emitter or collector, so that will be common between others too. Is it okay? So this is the collector, common collector. Now what are the points related to the collector, common collector? This is voltage buffer. This is voltage buffer. If collector common base is current buffer, so this is collector buffer. So in the case of collector buffer, AV is 1. If I'll talk about which type of source it is, so this is voltage control voltage source. The current buffer was current control current source, and this will be voltage control voltage source. So AV will be 1 and AI will be 100 for this. And this is voltage control voltage source. If this is voltage control voltage source, so R in will be in mega ohms and R out will be in 30 ohm and something. Is it okay? So for the common collector, the power gain is nearly equal to AI only. Is it okay? Now we'll come to the common emitter, very important one. Okay, let me draw the circuit over here. This is common emitter. In the common emitter, the situation is like RC, R1, RE, and here it's R2, like this, R2 is connected with input, and input is V in, like this, and this is this RC, and here it's VCC. Is it okay? So this is the common emitter. So one more thing is missing over here, and that is the parallel capacitor. Okay, so suppose someone will say you, what is the common in this circuit, and they are not applying this input over here and output over here, but the circuit is like this. So immediately you can judge the circuit by looking to the capacitor only. The capacitor is in parallel with RE. It means definitely it will be common emitter. Is it okay? This is common emitter, and common emitter is very important. Okay, among all. Why? Because the AV, if we'll talk about, is minus 200. We will talk about AI, so it will be minus 100. Right? So the power gain is due to, I'll talk about the power gain is will be AV into AI. So if you carefully observe this AV and AI, we are getting in negative. What the negative means? Means this common emitter is shifting 180 degree or giving 180 degree phase. Means in input and output we are having 180 degree phase, input and output. That's why we are getting it minus. Is it okay? So this is very important. Why? Because the power gain is very high into this. You can multiply this minus 200 with 100, so it will be like this. So this is 2 into 10 to the power 4. The power gain is very high over here, and the power gain is due to both AI and AV. Is it okay? So this is all about the common emitter. Now friends, we'll move to the small signal analysis, the very important part of the unit, the small signal analysis, right? So small signal analysis, see friends, wait a minute. This is the very important part. Again, I'm telling you, small signal analysis, because 60% of the question we are getting from this question only. If I'll talk about the BJT only, the BJT unit, small signal analysis. And basically we are using all this biasing and this circuit to amplify the small signals. Small signals basically will be AC only. We're having, very small signals. We have to amplify, and as we discussed earlier, we'll use the common emitter amplifier. Why? Because the power gain of the common emitter amplifier is very high. We have seen just now. Okay. So friends, actually what is going on over here, I'll tell you first, then we'll come to this theory part. Friends, this is the circuit kind of, like this is the potential divider biasing. We have chosen one biasing. Why we are choosing a potential divider? Because the potential divider provides us better IC stabilization. Okay. What is our, motto to use the biasing? Our motto is to stabilize the IC, the collector current. We need the constant current at the output, so amplification will be better, right? So the potential divider biasing is good for that. But if you'll observe this entire circuit, up to this part it's okay. You have knowledge of all this. This is the potential divider. You have a knowledge of this VCC, collector voltage. Okay, it's fine. But what is this CAs? What is this RAs? Why this parallel capacitor we are introducing with RE? This RL is fine. Why this CC is over here? And though this is the common emitter basic, and I told you, if this is the common emitter, there are two ways to find this. The number one is, check where is the input, where is the output. Here at the base region you are applying the input. At the collector region you are applying you are getting the output. So definitely it will be common emitter, no problem at all. But in other way you can identify by selecting this. The RE is parallel with capacitor CB. It means, what it means, the emitter is common. Okay. So one by one I'll tell you the importance of CS, CC and all, R1 and R2. Okay. Let me erase some part. So friends, what is going on over here? You are applying some parts, some AC parts, small signal analysis. You have applied over here some, let's take it V in. And at the output also you are getting the same thing, AC wave. It's amplifier or whatever, attenuated, whatever it is. But your purpose is, this is the amplifier. Let's assume that this circuit is amplifier. Means you are applying some input, you will get some output. Is it okay? Now what is the point? The point is why you introduce this thing. Earlier we discussed the Q point theory is very important. Right? If you want to bias something or you want to operate your circuit, it should be operated in the, Q region. Earlier we have seen the output characteristics like this. It should be work in this linear region. So there will be proper amplification. There will be no distortion. We have discussed about what if you will bias the circuit in such a way that Q point will be near to cutoff. What if you will be bias the circuit in which the saturation will be the Q point will be near to saturation. So in both cases we have seen some clipping to the original waveform or original signal, but when you choose the Q point at the middle of the load line, you are getting the perfect output input relationship. Is it okay? There were no distortion, there were no clipping at all. So once you choose this capacitor point, now your AC signal will fluctuate around this only at the output also. Is it okay? So for this you need to apply your input at this region only. At this region only you have to apply. For that we are adding some DC part into the input. We are shifting the level of input. We are shifting the input in such a way that your input will map to this linear region. Okay? Like this. Or your input will coincide with this linear region. So at the output you can the linear or the proper output. Is it okay? So you need to add some DC part. So by this circuit we are adding some DC part. How? Actually because of VCC, the voltage will drop over here. The voltage will drop over here. That voltage will charge the capacitor. How the capacitor will charge? Tell me. Wait a minute. Due to this potential divider biasing, there will be drop at R2. This drop R2 will charge the capacitor in this way. Let's take some voltage VC. Positive sign will be this side because this is the positive, this is the negative. Now your capacitor is charged. Capacitor charged means you are adding DC to your input. If I'll talk about this part, your input is V in plus VC. VC in means now you shifted your input. Very interestingly, by using this circuit, by using potential divider biasing, what you are going to do is you are adding your DC part to the signal. See, V in plus VC. Now V in plus VC is applied to the input to the transistor. Now because of this, your transistor is working in linear region, or your transistor is move in this linear region. Now you shifted your input. Let me take over here. Your input is like this. Here we'll get the output. Here is the Q point. Perfectly fine. Here we are getting output with proper shape. So at the output stage we are getting over here output. Is it okay? At the RC at this level you are getting output. But in your output, the DC as well as your small signal voltage, whatever you apply the input, both are there. At this point, if you'll talk about, not only your VN will be available with some amplified version, but it has some DC part itself, because at the input stage you added some DC part. Is it okay? So at the output you need only AC part, because this is the original input you applied. This CS or this DC part, whatever we added into the input signal, this is not original one. Okay. This was the magic of this circuit. So this is unnecessary thing for us. We don't want this. So again in the path of at this point voltage, we are adding some capacitor. We are connecting some capacitor. And if you remember, what is the function of capacitor? Capacitor will block the DC current. The capacitor will not pass the DC current. It will pass only AC current. This is the property of capacitor. It will not pass DC current. Why? For DC, capacitor acts like open circuit. Open circuit means R equal to infinity. Infinity resistance will be there for DC current into the capacitor. So it will pass only AC, whatever signal you applied at the input, and you will take the entire input in amplified way at the output. No distortion will be there, no clipping will be there if you choose your cue point at the proper place. I hope this is clear to you. Now I'll come to the theory part for this. Okay. Friends, CE, common emitter. Remember, common emitter is the very important. We are using that one only because the common emitter has a good power gain, a very large power gain, and it has 180 degree shifting also. So in the later stage we'll know why 180 degree shifting is also beneficial for us. So common emitter amplifier are very popular to amplify the small signal AC. After a transistor has been biased with cue point near the middle of the DC load line, this is the very important point and we discussed just now, right? AC source can be coupled to the base. AC source we are coupling to the base reason because the emitter is common. And at the collector we are taking output. AC source can be coupled to the base. This produces fluctuation in the base current and hence in the collector current of the same shape and frequency. Whatever distortion or fluctuation will be there at the input stage, the same will be at the output stage because of the proper selection of cue point, and the proper selection of cue point is the cue point should be in the middle of load line. The output will be enlarged sine wave of same frequency. The frequency will be same but it will be enlarged. Right? The coupling capacitor CC. Where is the CC? Here is the CC. This is the coupling capacitor. Why we are going to coupling CC? To remove DC part, right? So the coupling capacitor CC passes an AC signal from one point to another. At the same time, it does not allow the DC to pass through it. Is it clear? Hence it is also called blocking capacitor. So this will be blocking capacitor and this CS will be heading capacitor. Right? So the coupling capacitor acts like a switch which is open to DC and shorted for AC. Okay, definitely the collector capacitor, coupling capacitor will act like open circuit for the DC and will act like short circuit for AC. Means it will pass the AC, block the DC. Is it okay? Now the bypass capacitor CB. See, now see the bypass capacitor. The function of this is to block DC. To block DC. The function of this is to aid DC. Means I can say at the input stage you will add DC, at the output stage you will remove DC. Is it okay? So the bypass capacitor CB. The bypass capacitor CB is similar to a coupling capacitor except that it couples an ungrounded point to a grounded point. If the point is ungrounded, it will couple to it grounded. Why? Because the CB is directly connected with ground only. Why it will couple and how it will couple, we'll see here. The CB capacitor looks like a short to an AC signal and therefore emitter is set AC grounded. A bypass capacitor does not disturb the DC voltage at emitter because it looks open to DC current. As a design rule, XCB means the reactance of this should be 0.1 of RE. Means it is chosen like this, 0.1 of RE. It should be like this at lower frequency. So this is for stabilization, right? So this CB is actually used for stabilization of IC. IC stabilization. This is our fundamental goal, to stabilize IC, to make IC constant. So this CB will be help in this way. Okay. So this is the function of CB. The R1, R2 and CS, they will impose the DC into the small signal. The CC will block the DC at the output stage. The CB will stabilize the collector current. Is it okay? Now, this one is very important. If you are having AC as well as DC at the input, you have AC as well as DC before the coupling capacitor. So for this entire circuit, you need to study this circuit in two ways. You need to do AC analysis of this circuit and DC analysis of this circuit. We need two things to analyze for this circuit. One is DC analysis, one is AC analysis. In the DC analysis, we'll see how much voltage is dropping over here, or what is the value of voltage we are adding with the input, what is the collector DC current, what is the collector emitter current. So these are the DC parameters we can find out. And for AC, we'll talk about whatever signal we applied at the input stage, and at the output stage again we'll deal with the AC. So the DC is the mediator or the middle part of the circuit. It will not come to the input, it will not come out at the output. Is it okay? So based on this small signal analysis, we have two types of analysis, DC analysis as well as AC analysis. In a transistor amplifier, the DC source sets up Q current and voltage. The AC source then produces fluctuation in this current and voltage. The simplest way to analyze this circuit is to split the analysis in two parts, DC analysis and AC analysis. One can use superposition theorem for analysis, right? AC analysis and DC analysis. Very, 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 very important. Please focus on this. AC and DC analysis. First, I'll do the DC analysis. If I'm going to do the DC analysis of the circuit, what it means, AC circuit should be turned off. AC circuit should be turned off if you are studying or analyzing the DC circuit. If you are analyzing AC circuit, what you have to do is turn off the DC. Turn off the DC part. Is it okay? So we'll see over here. Let me erase some part, then I'll tell you. For DC equivalent circuit, reduce all AC voltage sources to 0 and open all AC current sources and open all capacitors. We are doing DC, right? So in DC, capacitor will act like open circuit. So we'll remove all capacitor, we'll remove all AC sources. If AC source is voltage source, we'll make it short. If AC source is current source, we'll make it open. You know it very well because we studied in circuit theory. So this part is clear to you. So for the DC equivalent circuit, reduce all AC voltage sources to 0 and open all AC current sources and open all capacitors. With this reduced circuit shown in the figure, DC current and voltage can be calculated. See, this circuit is obtained from the previous one only. Previous one, the circuit we have seen over here. Let me erase some part. What we are going to do, we are removing this part. Because this is the AC part, we are removing from the circuit. If you remove the capacitor, the RS will be useless. VCC will be here as it is. This capacitor will go out, so it will be remain with this one circuit only. So you can see here your circuit is just similar to that one. This is the DC analysis. If this is the DC analysis, you can find out everything. You can find out voltage over here. You can find out your IEDC. You can find out your ICDC. Everything you can find out. You can find out all DC parameters. So it will be very useful. Later we'll discuss about that. Now what about AC? For an AC equivalent circuit, reduce DC voltage source to 0 and open current sources and short all capacitors. We know about this. This circuit is used to calculate AC currents and voltage as shown in the figure. Now please observe this figure. This figure is also came from the original one. In this we eliminated all DC part of the circuit. See, initially the circuit was, let me draw over here. This is RS, V in, perfectly fine, and here I take V output. Is it okay? And here also I have capacitor like this. Now I need to do the AC analysis for this. For the AC, I'll short the capacitor. The capacitor is short. Here RS is as it is. This is the input part. But why this R1 and R2 they came in parallel? Why? Because this is C, right? VCC, this is DC part. We have to remove this, means you have to turn off this. So it will be grounded. These two things will be grounded. If R1 between this, suppose this is the point A to ground, R1 is there. This is point A to ground, R1 is there. A to ground, R2 is also there. So R1 and R2, they are coming into parallel over here. This part is over. Now your transistor is as it is. You can see over here. Now from C to ground, you are having RC. This is the C terminal. C to ground, you have RC. Fine. And this capacitor will be shorted. And there in the original one, you have load circuit RL, load resistance RL connected from C to ground. So this is the C terminal, RL connected C to ground. What about this capacitor? This capacitor is shorted. So if this is shorted, RE will be useless. So this is your circuit. This is your analysis, AC analysis. Now how to do it will come in the next video lecture. So this is all about AC and DC equivalent and DC analysis. But this is only theory part. We'll consider how to solve it in the next video. We'll meet in the next. Till then, take care and bye.